Alright, Internet, welcome back. So, we are going to work on Leviathan 5 and 6 today, as we did 3 and 4 yesterday. And these two are somewhat straightforward. I had to cheat on both, like usual, but I didn't have to cheat as much as I usually do, which is always nice. So, with this Leviathan 5, we're going to do two types of attacks. So, one weakness and attack we're going to use is symbolic links, which is level 5, and then level 6 is can be approached in two ways. Most people use brute force. I've seen one actually disassemble the code in assembly through GDB to kind of break it down. So I'll show you that answer. I can't really explain it as well as I wish I could, but you'll see all three. With that being said, let's get started. All right, so Leviathan 5. We will SSH into that one, and we'll need to use our password from 4, not 5. Don't make that mistake again. All right, cool. So I'm gonna move this out of the way so we have full screen-ish. All right, so this one here, if we do an ls, we can see that there's another executable in here. So we'll do another ls again, and this is the same thing I've said a million different times, but I'll say it again just in case you haven't watched other videos, is that here we can see that this executable has a set UID bit. What that means is that we can execute this, and if we execute it correctly, that means we get temporary root privileges, and we get to act as if we're Leviathan 6 and not Leviathan 5. So if we can execute this correctly, we can get root privileges. So the first thing I did on this challenge when I went through this, trying to troubleshoot it myself, was I approached it with strings first. So I said, okay, what strings in here that exceed 4 characters are somewhat useful to me? So if I scroll up to the top, I can see a few things here that are somewhat insightful. So we can see that in here, there's a few different functions being called. And in these functions, we can see that the set UID bit is being set. We can see a get UID happening. We can see there's a close of a file and open a file. There's puts and things like that. Anything else in here that's interesting? One other thing here is that we can see that there's a /temp file.log. It's stating that it can't find it, which is interesting. So those are some of the interesting bits. And then, of course, we're going to use ltrace, which is another thing that I've done when running this. So I tried ltrace. I said, okay, what happens if we do ltrace? Well, we can see here that a few things that are popping out that are useful for us to see and understand. And actually, let me get out of this. Run that again up here so it's easier for you to see. So up here we can see there's a few interesting things. So first things first is that it's looking to open a file, and it's looking to open that file in the temp directory, and that file is called file.log. It's reading that file here, and once it reads it, it's then going to put it in this location. So it's stating that it can't find what it's trying to put here. So that's interesting. So what if we go ahead and create that file and run it? That was the next step I took. So we're going to cd into temp, and we're going to touch a file called file.log, and we'll echo hello pandas into file.log. All right, so if we cat file.log, it has hello pandas. Okay, that's good. So we have our file, and we want to run it. So to run that, we're going to do this, and we will do file.log. All right, so it repeats hello pandas to us. So it looks like what's happening, and we know this from what we've seen previously, and actually if you try to run this again, it's going to cancel out because the temp directory that we have, I think, has a cron job in the background that either is based on time or actions, and it deletes those files consistently. So it's no longer there, so it can't actually find file.log once again, like we had previously. But back to the point I was trying to make is that it looks like what's happening here is whatever is inside of this file.log, it's being read into this executable, which is then read back out to us, which we saw was hello pandas here. So the trick here is what we're going to try to do is we're going to try to do an approach called a symbolic link. So a symbolic link is like anything on your directory. So if you're in Windows or Linux or whatever that is, you usually have a desktop, right? And on your desktop, let's say this is our desktop right here. On our desktop, we have a series of files and applications. So you can have like a trash directory, you can have, I don't know, Steam if you play video games, you can have some other application, and whatever there's there. And all these applications, most of which aren't actually sitting on the desktop. Most of these are shortcuts. Most of these shortcuts are linking back to the actual application, which is sitting elsewhere, not on your desktop. And this connection between what you're seeing on your desktop and what's connected to the actual app is called a symbolic link or a soft link. So we'll say soft. So these soft links can come in handy for us because we can actually create a symbolic link between the file that we can read from and we have access and permissions to, and we can symbolically link this to the file that we want the password from, which is going to be inside of the etc/pass_/Leviathan 6, right? So if we can actually symbolically link these two together, then once we run it through this executable here, it should then cat out our password here. Hope that was understandable. One thing I'll point out here is this article is somewhat useful to actually talk about linking and symbolic links, but I actually felt that, this video here by Learn Linux TV actually talks through symbolic links at a very, not super in-depth, but I mean 30 minutes worth of in-depth. So I thought that was very useful because in this video they talk about symbolic links, hard links, the difference between the two, the concept of inodes and how inodes are linked to hard links and not symbolic links. So I thought that video was useful. You should definitely check it out if you want to kind of understand what's happening here and why it's working the way it's working when we exploit this weakness in this file directory. Cool. So with that being said, we're gonna break in. All right, so what we want to do is we want to do a link, which is ln. Actually, let me clear this out. So we're going to do ln for link. We're going to do it -s or -- symbolic for symbolic links. And what we're going to do is we're going to symbolically link our, I think we actually have to do this one first. So we're going to go Leviathan 6, and then we're going to then create our file. And by doing that, we've symbolically linked the two. So now, if we run our program and we run it on the file we just created, it then spits our password out. And I think if I maybe cd into the file cd into temp, I'm wondering if I can see it. No, you can't. Okay, well, you can't see that in there. But anyways, like I explained last time, what we're doing in this kind of syntax here is we're linking. We're then going to symbolically link that with the -s here. We first want to decide what we're going to link to. So that's going to be our password file. So that's going to be under Leviathan 6. And then we're going to symbolically link that to the file that we have access to and the permissions that we can create. So when it runs through that program, it's then reading out the password from here because we've symbolically linked the two, which gives us our password here. So that is Leviathan 5. Now we have our password. We're going to truck on to the next level. So if we come back here, go to 6, put that in, and we are officially in Leviathan 6. Okie dokie smoky. So like I said last time, there's two ways to approach this, most of which every single answer I've seen is brute force besides one. So I wanted to call that out because I thought it was interesting that they approached it differently than everyone else. But first things first, let's kind of discover what's here. So we can see there's an executable, and we can also see that this executable has a set UID bit. Again, like I've stated previously, you can see that by the -s here, and also the highlighting red is useful as well. So we know we can run this, which is nice. So let's run it and see what happens. Okay, so we've run this, and it basically says that it repeats itself and states the application looks like it's looking for a 4-digit code. To better understand this, we can use our handy dandy ltrace, run this again, and we can see some more stuff. So it looks like there is they're basically replacing this for the 4-digit code that you input, because it's basically stating usage, the application, and then the 4-digit code you put in is then going to basically be pulled by this this %s. So we need to put a 4-digit code in, and we need to figure out the answer. And once we figure out the 4-digit code, then we get access. So if we actually run this and say 1, 2, 3, 4, it's going to say wrong. I put a plus in there on accident. See? But let's actually run this with ltrace to see what happens here. All right. So not much is useful in that regard. We can see that there's a function called ATOI, and that ATOI has our 4-digit code that we put in, and it might be comparing something here. So I'm going to show you the assembly answer, which I said I probably can't explain the greatest, but I want to show it anyways because I think it's really cool that somebody has done this differently. So what they've done here is they've run the program through GDB, and I'll kind of talk you through some of the stuff I do understand at least. So here we can see in this answer that they're running this through GDB, and this is basically going to break it down into assembly our application. And once it does that, they're disassembling on the main function, and when they disassemble the main function, they can then see what's happening throughout this entire process. So if we scroll down a bit, didn't mean to do that. Here we go. Scroll down a bit. You can see some stuff they've highlighted for us to kind of help us along with this assembly jargon here. I have a little bit of understanding of assembly, but not very much. So we can see that they've called out the printf. So there's some printf here. So you can see it's being called here. There's some movement here. They're doing another call. There's another call and then a compare. So this calls an exit at printf, but the compare is what we care about because the comparison you don't really see. There's another compare here, but I don't really know what that means. So we'll skip over that. We'll just jump to the piece that they talked about. So this compare here, you can see they're doing a comparison between this registry and this registry. So if we go down here a bit further, we can see what they're doing at the end of the assembly is they're basically taking the point of the plus 72 up here, where they're doing the compare. They're adding that to the main. They're going to then read in our 1234, which is our password. And once we've done that, we can see that they're basically going to do some magic here, which I think they're basically adding something somewhere because they found something. But yeah, they broke down the assembly and figured it out. That was probably the worst explanation you'll probably ever hear from anybody with assembly. You're welcome. And I'll get better at that someday. Okay, so now that I've butchered assembly, I'm going to walk you through basically all the other ways that others have done it, which is brute force basically. And with brute force, we're going to hit it with 4 digits consistently until we get the actual password. A few different implementations of this brute force. I'm probably going to use John Hammond's because it's the most straightforward and simple to do. There's another one here, which is pretty good, that you can look at. It's a very similar approach. It's using bash scripts to run this through. The reason I'm using John Hammond's is because he echoes out the kickback to see as it's progressing, which, it looks cooler. So I want to put the syntax in here so we can kind of walk through it quickly. So we're going to run a for loop, and that for loop is going to then run over basically every 4-digit comparison that we can find, basically. So we're going to loop through that, and then we're going to state that we want to do this, and we're going to echo. So we're going to echo out what's happening so we can actually see it unfold, which is always nice. And then we're going to run our Leviathan 6 here, and we're going to then input our characters that we've looped through, and then we're going to say done. Okay, so let's walk through this for a second. So we have a for loop here, and in this for loop, like I said, we're iterating over every single iteration of the 4 digits. So we're going to go to 001, 002, 003, 334, all the way up to 999. And once we've done that, what we're going to do is we're actually going to echo out the iteration that we're on here. So we're going to see 001 is the first one we've done. We're then going to incorporate that here. We're going to execute this, and once we've executed it, we're going to go back up and repeat it again until we get the correct answer. We've basically broken in through to another shell. And if we go back here, I'm going to put this in here. So we'll just type it out once more because, typing is enjoyable. All right, and then we're going to do this, but we want to echo it out. And one thing I can point out to you is this needs a dot. And let's go here. And say done. Okay. Before I do anything here, I guess I'll point out the fact that the reason we have these semicolons here is us chaining commands together. And that's something that we've come across in the past with other CTFs. We're actually doing command injection attacks, where you can actually connect a series of commands together with an input field that's not being filtered by some sort of application. So this semicolon is allowing us to chain these different commands together to create basically a small application that we can run directly inside of the terminal. So if we've done this correctly, if we do here, it's going to iterate, and as it's iterating through, you can see that it's basically trying all the different 4-digit characters that we can try until we eventually get to the correct answer. And it's interesting how it's basically running out of resources, which is that's pretty cool to watch. But we're pretty close to the answer, because I think it's around 7,000. And there we go. So it's 7123 is the answer, and you can see that it's basically put us in front of a $sign, which means we're inside of another shell. So if we run who am I, we can see that we're Leviathan 7. So if we then cat out our password, and it's going to be Leviathan 7, I think. Is it 7? I may have done this incorrectly. Huh. See what happens when you don't remember what it's called? It's actually Leviathan underscore pass, not pass underscore Leviathan. Not ass, pass. All right, Leviathan 7. And then we get our answer. Eureka, Eureka. So let's copy this and see, because I think the next, oh no. I think the next level after this is actually Dunzo. So let's just check that and confirm it. Yeah, see? Yeah. So we just LS, and congratulations. We've gotten to the end of the Leviathan series of challenges. So I hope that was useful. I know that it wasn't the best explanation for everything, but I'm sure that you hopefully learned some stuff, and we've provided some resources, so I'll see you around.